Damos inicio a nuestro segundo día de charlas, conferencias a cargo de expertos de diferentes países del mundo. La primera charla que vamos a tener el día de hoy es en inglés. Now I switch to English, and good morning, everyone. For me, it's a pleasure today begin with a professor and friend from the university where I complete my PhD, IMT Atlantic. IMT Atlantic is located in Nantes, France. And today we have the opportunity to listen to Professor Simon. And Simon, thank you for your time, thank you for your willingness, and for sharing with us your knowledge, and for the opportunity, and for your time. Thank you, Professor Simon. Before to start to the presentation of the Professor Simon, Simon is an associate professor at the IMT Atlantic. His research focuses on optimization and decision support for manufacturing and supply chain systems, with a particular emphasis on robustness, uncertainty management, and data-driven methodologies. He has coordinated and participated in multiple European research projects and has an extensive publication record in operation research and industrial engineering. Dr. Simon earned his PhD in operation research from the University of Geneva and holds an habilitation from Nantes University. Professor Simon, thank you for your time, for the opportunity, and it's a pleasure to see you once again.
Hi, Wilmer. Thank you for the introduction and thank you for the invitation. So I'm going to talk about constraint Markov decision process for multi-item inventory control. That's a joint work with Yosira Duliasac, who is a professor at HEC Montréal, and Eric Prescott and Thierry, we used to work in JDA. But in between the beginning of the project and the end, they changed company and they're now working at ServiceNow. And JDA was one of the motivation to start this project. Okay. If you're interested in my work, there is also a preprint available. So you can just type the title and you will have the document with more details. Regarding my presentation, I'm going to start by an introduction. So I will basically motivate the problem. And then I will define the problem, which is a multi-item inventory management problem with joint targets. I will explain a bit how we solve that problem, give some experimental results, and conclude. Okay, so our main motivation, as I explained, it came from JDA, which is a software company that is providing software for supply chain management. And they had one of their customers in the automotive industry who had problem to manage inventory of spare parts. And there are two difficulties with these spare parts. The first one is that spare parts are slow-moving item. So if you look at the demand for spare part or more generally for slow mover, it will look like that. So in this case, for January, we have no demand, February, no demand, March, no demand, and suddenly in April, you have some demand for 9 units. And then again, 0, 6, 0. So it's very erratic, and the demand is very low and very erratic. And this is very difficult to forecast. So spare parts is a type of slow mover. You find there are other types of slow mover. For instance, in the retail industry, you might think about these products. For instance, a very expensive electric toothbrush that nobody buys, but that the retailer has to have in the shelf because it's part of contractual obligations. And managing the slow moving items remain a challenging practice. I'm gonna show you why in a few seconds. And they also account for around 40% of the entire inventory of some company from a recent report survey. And here's why it's very difficult to manage slow moving items. What you see in that picture is the historic of demand. So in this axis, you see the quantities, and here is the frequency. So you can see that it's a logarithm scale. So for 0, the frequency is like 90%. And then you have some other orders that come with different quantities. And it looks like that. Now, if I try to to fit the classical probability distribution into that historic, for instance, with a normal distribution, it will not capture at all this observation, right? You have the distribution that is centered around 0, and that does not capture at all whatever is happening here. The same with the Poisson distribution. Negative binomial does a bit better, but not much. What works well is this, for instance, 0 inflated negative binomial, where you will basically look at 0 and first try to predict the probability of 0, in that case 90%. Then take the remaining observation and feed the negative binomial just for this observation. So in that case, you have a distribution that looks much better. Now, the problem is that when you look at the inventory management literature, all the work is focusing on these two types of distribution. They all make the assumption that, okay, the demand is normally distribution or follows a Poisson distribution. And that does not work good for slow-moving items. When you look at spare parts, there are even some very complex prediction methods, such as Bayesian models from Chapados et al., where they can account for the life cycle of the item and predict, like, for instance, because the car is 5, 10 years old, then the demand for spare part will increase. But this type of model, nowadays we are not able to account for them in inventory models. Okay, so what we wanted to do is to have an approach for managing inventory of slow mover, and we also wanted to be able to account for linked constraints among items. So that is one of the constraints for the customer of JDA. Typically, they have to respect a service level. That is, they have to be able to meet the demand on spare part based on inventory in 95% of the case. But this 95% is not per item constraint. It's a joint constraint over the several items. And that is something that there's not much method or literature on how to do that, how to have a constraint that links several items in inventory management. And so we wanted to have an approach that can manage slow-moving items and account for this constraint that link several items. And it can be a service level target, as I just explained. It can be other constraint like, you have a warehouse with a given capacity. So you have to make sure that the inventory level, the expected inventory level among all items is below the capacity of the warehouse. And so that's another constraint that links several items. So we had these two constraints in mind for the customer of JDA. And on the top of that, we wanted to have problem formulation that is generic enough to be applied in different types of customer. Yeah. So this is our motivation. Now we'd like to describe the problem a bit more in details. So we assume that we have a set of items, a set of K items, and we want to have inventory management policy for each of these items. And this inventory policy will be independent for each of the item. And the policy will look like that. So what we're going to decide is for each item K, when we observe an inventory level of I, what is the quantity we should order? Yeah, so that's the main decision, the order quantity for item K when the stock level reaches I. And basically this policy looks like a table where we have for each possible inventory level, the quantity that we need to order. And that type of table is very generic and it can model many other types of policies that are used in practice. So one thing practitioners very often use is the reorder point policy with a level. So with two parameters, small s and a big S. And how this type of policy works is that when the inventory level reaches small s, we order to replenish the stock up to capital S. For instance, if small s is 2, when I observe inventory level of 4, I do not order anything. 3, I do not order. When it's 2, then it's equal to small s, and I will order to replenish up till 4. So I order 2. When it's 1, I order 3 to get 4. When it's 0, it is 4. And basically, by using this type of table, I can model different type of policies simply by putting some restrictions on the table. Okay, so we have multiple items and we want to define the inventory management policy for each item. These slides give a bit more of intuition on what the problem looks like. So on this axis, you see the inventory level, and on the second one, you see the time. So at the beginning, the inventory level is here, and you see that as time goes, the stock level drops. This is because we receive orders from customer, so the inventory level is dropping. And at some point in time, we decide to place an order. When we place an order, we don't receive the product immediately. It takes some time from the suppliers to prepare the order and to ship it. And so the time between the moment we place an order and the moment we receive it is called lead time. And so basically, we place an order, the stock keeps decreasing until the moment we receive the product. At that moment, the stock jumps and the process continues. The inventory level will drop, place another order, and we receive it later in time. Now, the demand during the lead time is a very important parameter for us, because if the demand during the lead time is lower than the quantity I have on hand when I place the order, then when I receive my product, I will still have some inventory on hand. On the contrary, if the demand during the lead time is larger than the quantity I have on hand, then my inventory level will drop below zero, which means that I will have some lost sales or some backlogs. So basically, I will not be able to meet the demand. And this is bad, right? We want to be able to meet the demand from our customer. Having inventory is also bad because inventory have costs. There is a cost for the warehouse. There is a cost for the insurance of the product. And basically, all the products we have in stock, they cost money. And we can see the stock as money that is immobilized and that cannot be used for something else. So basically, whenever we can reduce the amount of stock, we are happy. And we usually try to find a balance between these two types of cost, the inventory cost and the lost sales cost. Yeah, the important parameter for us is this lead time demand, so the demand during the lead time. And we're going to assume that this lead time demand is unknown and follows the distribution with a discrete support. So we don't make much assumption about this distribution, just that it has a discrete support. So we have the possible values for the demand, 1, 2, 3, 4, 5, and so on. And then for each demand value, we have the probability to observe this demand. And by using this type of table, I can represent this complex zero-inflated negative binomial. I can also put this Bayesian model with this type of probability. So it's a very generic table, and I can model a lot of different distribution with that type of table. So then what we want to do is to find the policy. So the quantity to order when the inventory level is I for item K. And we want to find the policy that minimizes the expected cost. And our cost will represent also with a matrix that gives us the cost I have to pay when the inventory level is I and I place an order of quantity Q for item K. So it's just a big matrix. And in that matrix, I can model a lot of things with that matrix. For instance, I can model the holding cost, so that the cost for holding in stock 1 unit of item, and all I have to do is to multiply this HK by the inventory level, and I add this part to this CIQK. In a similar fashion, I can model backlog cost, stock out cost, a fixed ordering cost. It would be a cost I have to pay whenever I place an order, no matter what is the quantity. A variable unit cost, and yeah, those are the main costs used in inventory management. But you can think about other, like it's very generic. It's just a matrix that gives the cost when the inventory level is I and I place another Q for each of the item K. So I want to find the policy that minimizes the expected cost and that also respects a joint target. Actually, we can account for several targets. So the M here, the index M is the index of the constraints. We can have several of them. And for each constraint, we have a capacity, Rm, and we have the consumption that is also given as a matrix. And that's the quantity of the constraint that we consume when the inventory level is I and we place an order Q for item K. And this joint target can also model a wide range of situations. The constraint looks like that. So we sum over all item, all possible inventory position, and all quantities. The consumption times the probability to observe inventory level I and order Q. So that depends on my policy. And that should be lower than the upper bound. For instance, if I want to model a bound on the average number of orders, what I do is I set this phi to 1 when Q is larger than 0 and 0 otherwise. And with that type of constraint, I can model many different targets that we encounter in inventory management. For instance, I can have a probability of stock out. So I can say that I want the probability to have a stock out to be lower than 95%, for instance. Another one, for that, I just set the phi to the probability that the demand is larger than I. The same, I can have service label based on the fulfillment. I can have the maximum expected number of order or a constraint on the inventory level. And so those are constraints that links several items. Okay. So now my problem I can model as a Markov decision process. In the Markov decision process, you have three elements. You have states, action, and probability of transition. The states in that case is just the inventory level. So I have here's a very simple example with just two states. Inventory level is equal to 0 or inventory level is equal to 1. Then in each of these states, I can take two actions. In that case, I have the action order 0 unit or order 1 unit. And then the transition matrix will tell me, given the state and the action I take, what is the probability to go back to state I is equal to 0 in that case. So if I'm in state I is equal to 0 and I place an order of 1 unit, the probability to go back to state I equal to 0 is equal to the probability that the demand is 1. The probability to go to state I is equal to 1 is the probability that the demand is 0. And I can have like that the full transition matrix. For each action state, I have the cost, so that the matrix I was talking about, and we have the consumption on each of the constraints. So I can model this problem as a Markov decision process, and yeah, and we're going to optimize, try to find the policies that minimize the expected cost over an infinite horizon. To solve the MDP, there are approaches. The most known approach are like dynamic programming, policy iteration, or Q-learning. These are well-known approach, and an approach that is less known is the linear programming approach. So we can solve an MDP with a linear program. It's not new, it's old, but it's not as well known as dynamic programming. And the approach work based on what we call the occupancy measure. And the occupancy measure is the probability to be in state I and take action Q. And this occupancy measure, it depends, of course, on the policy that I choose. But of course, it has to respect the transition matrix. So what we do is we have a decision variable, which is this occupancy measure, and we have a set of constraints that make sure that this occupancy measure that is selected by the solver is a valid probability distribution and that it respects the matrix of transition. I'm going to show you how it works with a bit more details afterwards. But basically, if I compute this occupancy measure, then from it, I can derive the policy that I want to follow. And this policy will be non-deterministic policy in general. So given the occupancy measure, the policy will say order Q unit with probability, the occupancy measure basically normalized. So what we have at the bottom here is just the sum over all action of the X IQ of the occupancy measure for the level I. So we directly have the policy from the occupancy measure, but it's a non-deterministic policy. The linear program, it looks like that. So we have an objective function, where we try to minimize over X. So the occupancy measure is a decision variable. It's a variable we try to optimize. And the objective function is to minimize the expected cost. So the sum over all state and action of the cost times the occupancy measure. And then we have this constraint that makes sure that the X here is a valid occupancy measure. So basically, the probability has to be positive. The probabilities have to sum up to 1. And this constraint here, it makes sure that we respect the transition matrix. Basically, what it says that the left part, before the minus sign, is the probability to be in state I. And the probability to be in state I should be equal to this part, which is the probability to enter state I. And the probability to enter state I is basically the sum of all state J, all action Q, of the occupancy measure times the probability transition matrix here. So that the probability to, given that I'm in state J and I take action Q, to go to state I. So this line here makes sure that I respect the transition matrix. Yeah. So when I solve this linear program, I can solve that with simplex algorithm. It's solved quite fast. It's actually implemented in many software such as Cplex or Gurby, and we can solve that quite fast. The issue we'll face is that as the number of action and state grows, the size of the model will grow and it will not fit in memory. So that's the same issue we'll have with dynamic programming. It's a curse of dimensionality, but it works quite well if the action state is not so large. So now that's it for just one item. Now what I'm going to do is I'm going to create this MDP for each of my items. So I'll create multiple MDP, and I'm going to add a resource constraint. So to create multiple MDP, I just write the constraint for each of my items, and my objective function, I just sum it up for all of the items. So I get like that one linear program that will solve all my MDP. So one MDP for each of the items. And on the top of that, I will add my linking constraints. We'll make sure that the occupancy measure are such that it respects each of the joint target constraints. Yeah, so as I said, we can solve that, and it works well. We get a policy out of it, and as I explained earlier, this policy is not necessarily deterministic. Here, I explain a bit more clearly what a deterministic policy and what is a non-deterministic policy. So in deterministic policy, for each state, you have just one clear action you can make. So if the state, if the inventory level is 1, I will order exactly 1. If my policy is non-deterministic and I have an inventory level of 1, the policy might tell me, okay, you can order quantity of 1 with probability 0.25 or 2 with probability 0.75. And okay, there are two things about this non-deterministic policy. The first thing is that the optimal non-deterministic policy will always be better than the optimal deterministic policy. And the way to see that is that you have more non-deterministic policy, and the set of deterministic policy is included in the set of non-deterministic policy. So when I optimize for this set of non-deterministic policy, I always get better solutions, better policy, than when I optimize for just deterministic policy. That's the first part. So it's better to use, in terms of cost, it's better to use non-deterministic policy. But it would be very hard to go to a practitioner and to tell him like, look, when you observe an inventory level of 1, if you want to know how much you need to order, you will need to throw a dice, and depending on the result, you will order 1 or 2. Usually, a practitioner will not accept this type of policy. Yeah. So to sum up, we have a nice and generic formulation. We can solve many inventory problems. It solves quite well as long as the size of the action state space is limited. On the downside, the policy we get is non-deterministic, which is not nice for practitioner. They're also based on table lookup policy, and sometimes practitioners they prefer to have, this reorder, this SS policy that I was talking earlier. And you also have some scalability issue. Now, in the next few slides, I would like to talk about how we can solve these issues. Regarding the deterministic policy, what I can do is I can add to my linear program a few sets of variable and constraint that will force to get a deterministic policy. But there is a cost for that. I need to add this variable, which is the binary, takes value 0 or 1. And then I will just make sure that my occupancy measure, this variable basically tell me which is the action I take for inventory I on the inventory level I. And this constraint here makes sure that the occupancy measure respects this policy. And so when I include this variable and constraint, I get a deterministic policy. But the problem is much harder to solve because I cannot use a simplex algorithm anymore. I need to use more complex methods such as branch and cut or branch and bound, which are more time consuming. Okay, so what else can we do? We can use an algorithm that's called column generation and branch and price. And yeah, the way it works is that we're going to reformulate our problem. So we're going to make the assumption that we can enumerate all possible policy, and we'll have a program that will decide which is the policy to use. Of course, in practice, we cannot enumerate all policies, so we generate them iteratively with the column generation framework. So what do I mean by generating all possible policies? So you might have a first policy that tells me that for any possible inventory level, I order Q equals 0. Another policy, when inventory level is 0, I order 1, 0 everywhere else, 1, 1, 0 everywhere else, and so on. So I assume that I'm able to generate all possible policy. Now for each of the policy by k, I can compute the cost of using that policy, and I can compute how much that policy will consume on the resources. Now what I can have is I can have a program that will just select which policy I use for each item in such a way that I minimize the expected cost and I respect the resource consumption. And yeah, as I explained, enumerating all policies is not feasible, so we do it iteratively. So we have a master problem in which we will have a subset of all policy. We solve for this subset of policy, and then we solve a subproblem that will that take as input dual information from the master problem and generates a policy that has the potential to improve the current solution. And we iterate that way until the subproblem tells us that okay, there is no more policy that can have a chance to improve the expected cost. So that's the column generation framework. When we solve it, we still get a non-deterministic policy. However, at the very end, at the last iteration, when I have generated a subset of interesting policy, I can solve a last time the master problem where I will ask it to restrict to just deterministic policy. So that's the heuristic version of column generation. The other approach is to incorporate the column generation into a branch and price algorithm that that will run column generation several times until it finds the best deterministic policy. Another thing that I can do is I can modify the subproblem and I can restrict it to solve only for specific types of policy. So I can ask the subproblem to solve only for SS types of policy. And we even have an algorithm that's able to do that with a pseudo-polynomial complexity. What I can also do is this subproblem not solve it to optimality. And so I can rely on local search, for instance, to solve the subproblem. And the very nice thing with that is I can also, when the action state space is too big, I can evaluate the cost of the policy not exactly, but with Monte Carlo. And when I solve this subproblem with local search, I can really solve for very large scale problems. Okay. And I would just like to give you some of the experimental results. What we did is we generated some instances. So as I explained at the beginning, we have an approach that can solve a wide range of inventory management problem. In that case, we just focus on 3 types of costs: the holding cost, setup cost, and unit cost. And we impose 2 constraints on our inventory management policy. The first one states that for each of the item individually, the stockout probability should be lower than 10%. So in 90% of the case, I want to be able to serve my demand from stock. And I have a second constraint that goes across all items that says across all items, I should be able to serve my demand based on the stock with priority 95%. Okay. An important parameter in my result is the aggregation level. So the demand, as I explained, we take as input the lead time demand, which is given as a table. And for each possible value of the demand, we have the probability. And this demand table can be very large, right? If you have a table that goes until 10,000, that start to be quite large. So what I can start to do is to aggregate the demand. So I have an aggregation factor, tau, and in that case, it says that this demand 1 and 2, I will aggregate them together, and they will become 1 tau with probability 0.08 plus 0.12, 0.20. The same, I can aggregate these two, and these two. So basically, I aggregate the table. I lose a bit of precision, but it helps to reduce the size of the state base of the action state space, and so it helps to solve faster the problem. Yeah, so this aggregation level is an important parameter that I will show in the experiment. For the experiments, we use a time limit of 1 hour, and we limit the memory to 10 gigabytes. And here you have a comparison between the three approaches, the linear programming approach or the branch and price, which is based on the column generation. What you see here is the number of items, so 10, 1,000, 100 or 1,000, and number of feasible is the number of cases for which we can actually solve and get a policy. So when you have only 10 items, 8 out of 9 times, I get a solution, so I'm able to solve. Whereas when the number increases to 1,000, only 4 out of 9 times. And it's a bit better for the branch and price and column generation approaches. What you can see as well is that in terms of quality of the solution, this branch and price approach is more stable. It's in the gap, the percentage gap between the best policy we've found and the policy found by the method. And it remains below 2% for branch and price. This one is a branch and price where I restrict the subproblem to find the SS policy. Okay. Now we have the same table, so there's three same approach: the mixed integer program, branch and price equipped with the SS policy. But what you see on the left is the aggregation level. So here I have no aggregation, so tau is equal to 1, tau is equal to 10 or 20. And what you see is that with an aggregation of level of 10, with the branch and price approach, the two of them, with the table policy or with the SS policy, I can basically solve all instances can solve all instances. And now if I want to solve with the aggregation level of 1, what I can do is to use the approach with the column generation where I solve the subproblem with local search using Monte Carlo. In that case, I can solve all instances. It works quite well. Okay, just the last result before to conclude. So what we did is we generated some data to represent the demand. And we split the dataset in two. A first part to fit the distribution and to optimize the policy, and a second part to simulate the use of the resulting policy. What you see in that type of graph is the aggregation factor, so 0, 5, 10, 15, and so on. And here you see the relative policy cost. So for aggregation level of 1 is the base case, so we set it to 100%. And then when the aggregation level is set to 2, it means that the cost reduced to 96% of what they were for 100. And there are two things here. On the one hand, we first feed the distribution. And when we feed the distribution, having a large aggregation factor helps. In that case, we use an empirical distribution. And the 52 here is the size of the historic we use to train the distribution. And for the empirical distribution, the more we aggregate the demand, the better is the fitting of the distribution. And so we get better results. However, when we have a large aggregation factor, for the optimization step is not so good because we lose some accuracy. So there is a trade-off to find. And so with the empirical distribution and 52 weeks to train of training data, the aggregation factor of 5 is the best. Okay, you see that the 26, 52, 104, and 208 here are is the size of the historical data. So what we see is that when the amount of historical data I have increases, I can have a lower aggregation factor and better results. This is what happens when we use a parametric distribution, so zero inflated negative binomial. So we see that in that case, the aggregation factor still help, but less than with the empirical distribution. So in that case, even when you have 4 years of data, you don't really need the aggregation factor. Okay. And so to conclude, so what we have is we study a multi-item inventory optimization problem, and we solve it with couple constraint Markov decision process that allows us to generate inventory policy that can account for multiple targets that cross over multiple items. We have an approach that that works well that doesn't make any assumption on the distribution, and so we can use it for slow-moving items. For future works, what we would like to do is to also consider constraint not on the average resource consumption, but on the expected resource consumption. So basically, instead of having the sum over all items here, we'd like to make the expectation, so the multiplication here. That's a bit harder to solve because this is not solvable with linear programming. So that is left for future works. Yeah.
Okay, Simon, thank you. Thank you for your presentation. We have time for maybe for 1 or 2 questions. The first question is the people ask in the work that you present, have linear programming models been combined with the stochastic approaches such as Bayesian models?
Well, we tried that, but we didn't present the results. So we can combine it, and it works fine. It's just that you have your Bayesian model, and then you translate it to the demand table, and that works quite fine. So we had some study on that, but we didn't keep them for the final results.
Okay, perfect. And the last question, and what software did you use to implement the policies?
So what we use is Python to implement the simulation. No, sorry, it was in Julia. Julia for the implementation of the simulation and the policy, and then to solve, we use Cplex to solve the linear program.
Okay, Professor Simon, thank you for your time and for the opportunity.
Thank you for having me, and it was very nice to see you, Wilmer.
Bye-bye, Simon. Thank you.
Bye-bye.